Okay, hello everyone. Nice to see you all. This is the IEA Wind Task 43 Metadata Challenge webinar series number 2. And we're very excited to have Julian with us today from DTU Wind, who's going to talk about how rich metadata schemes can allow for better designs via optimization under uncertainty. So the plan is, as usual, I'm just going to do a very short introduction about what the metadata challenge is for those of you who don't yet know. And then the most of the time is going to be spent with Julian telling us about his topic. And then we're going to have a decent amount of time for a discussion. And then maybe there'll be some closing remarks or something that we want to do together, or a little collaboration or a little project that somebody wants to do together or something. The idea is that we generate a nice discussion and build up a community of people interested in this topic. So does anyone have any questions or anything they want to say before I do my short introduction? I think if you want to speak during the presentation, maybe we can just ask Julian what he'd prefer. Like, would you prefer chat comments? Would you prefer people just to talk? Would you prefer silence until the end? You want to say?
Yeah, I think if we can just have a friendly conversation together, that'll probably be best. I mean, I'm reserved the right to say, well, that comes in a couple of slides, but I think it would be best just to have a friendly conversation.
All right, that's good. Am I sharing the right screen?
Looks pretty good.
All right, good. So I'm not sharing the video of you, I'm sharing the slides. All right. So yeah, just a quick introduction about IEA Wind Task 43 Metadata Challenge. So IEA Wind Task 43 is part of this thing called the IEA Wind Technology Collaboration Program. And there's many different tasks, and digitalization is just one. There's a link there, which I can put in the chat later, which is telling you more about the task. We have lots of things that we're doing. And one of the things is looking at data standards and sharing. And in the metadata challenge, we've kind of focused on the topic of metadata. We've redefined the goal recently. So the goal of this challenge is to research into metadata and knowledge engineering for wind energy applications, and then use the results to develop recommendations for the sector. We've got 4 different sub-challenges, which are being led by different people. One of them is about managing metadata schema. The other one's about defining schema for data and metadata. The other one's just reviewing existing works and what's been done in the community so far. And then D is more like the politics, long-term things, communication. And as part of D, we've recently launched this public webinar series because we're really keen on improving the collaboration between knowledge engineering experts and domain experts in the area of wind energy, because we've kind of defined that as a thing that is maybe missing in order to advance wind energy further. So why is knowledge engineering important? Well, basically, okay, digitalization is important because it's one of the key drivers for reducing the costs and risks over the whole wind energy project life cycle. There's an example publication from Wind Europe there, but there's many other things that people talking about that. So what's an opportunity that digitalization can bring? It could include things like digital twins, predictive maintenance, drones, AI systems. These can all contribute in different ways to reducing the maintenance costs and also increasing the amount of energy delivered. But for these solutions, we don't just need physics, simulations, and data analytics. We also need AI systems to process, interpret, and perform logical operations on structured data, which is known as knowledge engineering. But we also need the structured data itself that represent information so it can be used by these systems, which is known as knowledge representation. What are we trying to do here? Are we trying to improve our understanding of all these terms and all these things? So first of all, what do all these words mean that are used in the knowledge engineering domain? We have quite a lot of discussions about the exact meaning of metadata and taxonomy and ontology and semantics and schema, etc. And we've started a very nice glossary, which is work in development. I can put the link in the chat as well later. But the other questions we've been asking ourselves, why do we need to know these things? Or how can we help people understand why they need to know these things? What's been done so far? How can we utilize that? What can we learn from knowledge engineering experts? What can we learn from other domains? Also, how can they maybe learn from us? Because wind energy is quite an interdisciplinary area, so we might have some nice use cases for other people to learn from. And then also, how can we work together? So these are all the sort of things we're trying to work out in this challenge. So to the topic of going into the topic of what Julian's going to be talking about today, quantifying uncertainty is really important, and for many different applications. So, for example, if you want to have a bankable wind resource assessment, you need to quantify your uncertainty. If you want to do a wind turbine design or a type certification, also if you want to make optimal operation and maintenance decisions. And there are some researchers such as Julian who are increasingly carrying out this thing called optimizing under uncertainty, which is basically assessing the impact of various input uncertainties on different outputs. And this information has to be captured in the metadata, as Julian's gonna explain in more detail in a minute. And this uncertainty metadata can then enable a new generation of risk-informed designs via optimization under uncertainty. So I'm going to pass over now to Julian to tell you a little bit more about what that all is. So yeah, go ahead, share your screen, and I'll mute myself.
Great. Does everything look okay?
Yeah.
Great. Well, thanks for that great introduction, Sarah. I think that was a really nice preface to what I'm going to talk about. And before I really dive into the presentation, I guess I'll give this motivation slide. And I think the picture I want you all to have in your head is this top image where we have when we're dealing with a digital project, we have a bunch of digital objects, which are sort of like Lego building blocks. And through proper data management, through a lot of planning and negotiations with different people, we can organize our data into a sensible way. Then after this organization is achieved, we can build a data product. So when we're dealing with a small project, we can sort of do all these little details manually. Like if I'm growing a small soybean plant or something, I can pick off the aphids and make sure it's all taken care of well. But on a large scale, we have to do things in an automatic way. And we want to make sure we can still trust the systems that we use. So that's what I'm trying to get across with this picture. We have these different Lego blocks, and we want to make a beautiful product in a machine-friendly way, in an automatic-friendly way. And in particular, what I want to represent with these Lego blocks is metadata, things that provide contextual information about the data. And in this talk, I'll focus on information about uncertainty, as in what we know and what we don't know. So this business of organizing Legos, in this talk, I'll call it data or metadata management. And whether or not people realize it, every organization has some sort of metadata management scheme. And this is an important business strategy. And when you look into other sectors that have really embraced big data, I'm thinking about LinkedIn, Facebook, PayPal, things like this. This organization comes with concepts of schema, taxonomies, or ontologies for seamless integration. And I will talk about exactly what I mean by these three things in a few slides. So my talk's sort of about two things that are very related. First of all, we want to trust the processes that we have automated. And we can quantify trust by quantifying uncertainty. And then secondly, we want to have automatic processes that scale well. So data management and sort of the metadata paradigm allows for this scalability. So I'm sort of talking about the scalability of trust, if you really want to simplify it. Anyway, in our sector in wind, there's this great need for understanding uncertainty, understanding risk, and establishing trust between forecasters and stakeholders. There's limited information available when predicting very complex phenomena, like, imagine measuring the wind speed in a field and predicting how the wind will blow for the next 20 years. I mean, I think we all understand that this is something riddled with uncertainties. However, this is exactly what we do. So in this picture, I'm showing an image taken from this report. It came out in 2016, sort of showing what was the state of the art then of predicting AEP. So there'll be some gross estimate of the annual energy production, then some predicted losses based from wake effects or other things. And so the industry knows that there are losses that will be taken into account. There is uncertainty that can be estimated, but maybe because of perverse incentives or maybe because of ambiguity in some of these processes, there is a tendency to overestimate the AEP. And anecdotally, I've heard that this gap has been reduced from 10% to 5% in the last few years. But I don't have the latest and greatest data on this. But I understand that there's a problem around over-predicting AEP and also the methods for quantifying the spread of uncertainty versus, the range of possible annual energy productions versus the measured annual energy productions. It could be more comprehensive. And then I also want to say that there's an opportunity here. Businesses that understand risk in a very comprehensive and science-based way can gain a competitive edge, either through being able to make more informed investment decisions, or even by being able to offer warranties on their products. And of course, a warranty will come with a surcharge. And just, want to talk a little bit about the basic philosophy of quantifying uncertainty. I mean, if we add new measurements, like if I have a new Met Tower Met Tower or a few more years of data, my uncertainty should somehow go down. Like we should have less uncertainty from new measurements, as long as they're very good measurements. As well, on top of this, if I reduce my potential measurement error, that should reduce the uncertainty in my model. And finally, we should avoid assuming a model to be reality. Instead, take a more Bayesian approach. So as a fun example, let's say I have some sort of shear profile model that predicts the wind speed as a function of height. And then here's what I actually measure in white. So these things are very different, but because I've taken this sort of Bayesian approach in this toy example, I still encapsulate what the truth might be. Granted, my model is very off, and we might want to have some conversations about that. But at least I'm able to say something useful with my uncertainty predictions. And I just want to go through a brief example of actually applying these ideas, because I think it can be very abstract sometimes. So I'll just go three or four slides about some of my work applying optimization under uncertainty to wind turbine control strategies. So in this example, I have a turbine in the front, turbine in the back. The wind flows from left to right. The darker colors indicate the wake. And we want to offset the front turbine so that the wake steers away from the back turbine. Oops. So this is a low fidelity model. We understand that this is not a perfect representation of reality. Still, it can be useful to quantify the effects of using this tool for designing with or without reasonable uncertainties and potential gains in our production from taking uncertainty into account. So what am I talking about with optimization under uncertainty? I mean, I hope this slide will clear that up. Typically, optimization engines will query a simulation, which return a quantity of interest. Like this might be the layout that I'm changing and putting into my simulation, and my simulation might return AEP. This new way of thinking about designing things actually embraces the idea that we don't really have a perfect idea of what the AEP or objective will be. Instead, there's this range of possibilities. So I'll query an uncertainty quantification routine with my turbine layout. Then this will query my simulation many times with many possibilities of the way that the environment might be, the way that the turbines might respond to the environmental conditions. And then I'll have a range of possible annual energy productions. And I can take a statistic of that range and return it to my optimizer. So instead of optimizing for just a single value, I optimize a statistic, and I want to say maximize the 10th percentile of AEP, or whatever your favorite statistic of AEP is in this example. In my wake steering example, I'm just looking at the average power, just to give a as simple example as a fairly simple example for in the wake steering context. So I'm showing just the same setup as before, 2 turbines, and I'm changing the front turbine's yaw offset. And I'm using an engineering wake model to predict the power production in the front, back, and total and whole wind farm. So these colors represent different amounts of uncertainty in the wind direction. So red means more, you don't know which way the wind is blowing, and blue means you know exactly which way the wind is blowing. So uncertainty in the wind direction decreases the projected area of the front turbine, decreasing power production. But this interesting thing happens. The uncertainty in the direction sort of creates uncertainty in where the wake will be from the front turbine. So that can be thought of as spreading the wake out. The wake is less concentrated in a single point and more spread out as we have more uncertainty in direction. So these crosses indicate where the optimal front turbine yaw offset is. And what they're saying is if you don't know which way the wind is blowing, don't steer. So I hope it makes sense. The uncertainty in direction has a very profound impact on the performance of wake steering strategies. And I think there are some controllers nowadays that actually take this uncertainty into account very explicitly. So in the study, we looked at different parameters and did similar studies to this, as well as a full wind farm case. We found that wind direction was by far the most important uncertainty to consider, which sort of makes sense. We're steering the wakes in a somewhat precise way, or we hope to. And when there's less precision in the inflow direction, that affects the precision of our design. When I was quantifying which parameters mattered the most, I had to go through data I could find and quantify reasonable uncertainty distributions for these parameters. In practice, in the closed loop control strategies I mentioned, these uncertainties are updated constantly, both based on measurements in real time, as well as prior information from long-term campaigns. For yaw offsets, I actually had mast in front of my wind turbine. I was able to directly measure it. Still, these distributions that I found for my uncertainties are very much a first order approximation. And if an organization was to really dig into this, I think that they could find many conditionalities to these distributions, and a lot of details could be fleshed out. So I guess what I want to say is the uncertainty distribution we use really matters here. And it might be tempting to say, okay, well, I don't know, my wake expansion coefficient and my direction is uncertain. And that was my job. I found the uncertainty for you. But we should embrace that the parameters of a model are not really encompassing the full uncertainty of the model. There is just the discrepancy between the model and reality. And that is what we really want to target. So in the wake steering example, many closed loop controllers actually, or some, I guess, I've been told at least, this stuff is kind of proprietary. In the literature, at least, there are some strategies that build a discrepancy function between the model and the reality that is updated based on measurements. And this discrepancy function, as well as parametric uncertainty, allows to understand the full range of model outcomes. So this brings me to a bigger point. I mean, these methods are only as good as the uncertainty distributions that we pick and that we calibrate. So this isn't arbitrary. If it feels arbitrary, something is going wrong. This is sort of the basic workflow I see for managing uncertainty in the context of wind data, probably for an enterprise corporation, but for smaller entities as well, or for a researcher as well, although this will have to be more broad necessarily if you have a wider audience. So first, use data to calibrate your uncertainties. Say I have a model and I want to calibrate this data. Those of you that are in the world of mathematics might recognize this problem. Next, I want to propagate my calibrated uncertainties and ideally perform a validation campaign. So if I have measured outputs in a model, I want them to match. So you can see my model and my measured outputs. They don't match too good right now. So I would not be happy with the uncertainties I've developed, and I would not feel very good about performing optimization under uncertainty with these results. You want to validate your uncertainties so that they are trustworthy. This whole notion of optimization under uncertainty is to build trust. So you want to have trust in your underlying distributions. And there are very well-established frameworks for validation, verification, and calibration to accomplish exactly that. So earlier I said that schema fit into this somehow. So what do I mean by schema? Schema is sort of a blueprint of what data should look like, an expression of descriptive and structural metadata with defined semantics. So in this example, I'm thinking of a met mast, like a meteorological tower, and I'm thinking of what schema I might have. So there'll be measured data as a function of time, then some maybe core piece of metadata, like who owns the data or where the met mast is located. Then metadata surrounding the instruments, maybe the heights, orientations, the boom lengths, the models, the manufacturers, perhaps the warranty information for the equipment we bought or the maintenance schedule. And also some specification of uncertainty in our measurements. I mean, the manufacturers give uncertainty sheets. I've seen them. They are often conditional on the wind speed that is measured. That should be included in my ideal met mast schema. And maybe some information about obstructions too, like if there's a barn nearby or something, that will be useful. And this is by far not comprehensive. Like if you really wanted to dive into it, in task 43, we've identified 4 broad types of metadata. And we keep saying the more metadata you have, the better it will be for everyone. It really enables a lot of context to be gained, a lot of new information or information that's important that might be lost without having a comprehensive schema. So my talk really focuses on the importance of uncertainty, but I hope you'll believe me that these other things are useful to have in your schema as well. So one thing you might be thinking is, well, that sounds great, Julian, but my schema doesn't look like that. I mean, what is to be done about this? And that's where ontologies come in. Ontologies allow for schema to be modular. I mean, earlier I talked about putting Legos together. What's awesome about Legos? They're modular. They fit together in different ways. How can we make schema modular? This is kind of an advanced topic, and I know that you might not get this right away, but I just want to expose you to this. I mean, I talked to a lot of very smart people, and a lot of people take some time to wrap their minds around the idea of ontology. It's a new concept for many people, so it's okay if you don't 100% get what I'm talking about here. But I want you to know, ontologist is a job title in the tech sector. Facebook, LinkedIn, PayPal, they pay people to build ontologies so they can have modular schema. It's something that's recognized as being very useful when working with data in industries that are very mature in terms of data. So exactly what do I mean by an ontology? Well, I mean something that relates different concepts using logical operators. So here are the logical operators that I'm talking about. And when it's just a subset relating different concepts, then it's a taxonomy. So for example, in my met mast example, there are several anemometers in my MetMask, so they should probably all have their own schema. And then I want to have this like core schema, maybe the Dublin core that has the author and title, things like this. Every anemometer should be attached to a core schema, but every MetMask, or the MetMask should also be attached to a core schema. So how do these things all fit together? Then I my turbine that I'm eventually going to install, it has anemometers on it. So it should be attached to the anemometer in core schemas. But the uncertainty in the anemometer, it's different when it's on a turbine than when it's on a MetMask, because turbines have rotating blades in front of the anemometers. So how do you encode that there's different uncertainty information? You can encode this through a ontology. I've found a few ontologies that have been proposed for different areas in wind. I've listed 5 of them here. My perception is that it's still somewhat early, and there's a lot of opportunities for advancing the state of the art in terms of allowing for modular schema like I'm describing in my MetMask example. So I'm getting towards the end of my presentation now. I guess I want to send the message that investing in metadata infrastructure can have really powerful downstream benefits. And in our case, I focused on risk-aware design. So having strong schema, strong ontologies, strong semantics allows us to acknowledge and embrace connections between different information sources. I mean, there is a relationship between the uncertainty in an anemometer and the uncertainty in, or sorry, the uncertainty of an anemometer on a turbine and the same model anemometer on a MetMask. There are many relationships such as these. Take SCADA data on turbines, for example. There's hundreds of thousands of SCADA variables. They all mean different things depending on which turbine manufacturer you're looking at. There can be the same vocabulary that means different things, like if a brake is applied or not when deregulating power, what have you. And we can be modular. We can treat our schema like Legos using ontologies, but we have to build the ontologies first, which takes time. So if anyone's thinking about how to be strategic with what data they collect and how data is connected, I would recommend investing in metadata schema and perhaps ontology development. So that's kind of the end of my presentation. I hope I'm making any sense here. The basic messages I want to send are that metadata schema allow for the strategic scoping of data campaigns, and that there is a lot of information to be gained from uncertainty metadata. And this uncertainty can enhance trust in the design and analysis process. And when we have trust in our uncertainty that we've learned, we can employ risk-based design, which can really change the way we think about design. And like Sarah alluded to, it can be sort of this next generation of designing mindsets. So thanks very much for listening. Here's my email if you want to get in touch with me. I'd love to continue the conversation. Let me know if there's any questions.
All right, thank you very much. Thanks for the clapping, Yuri. I can't hear it, but I can see you clapping. Yeah, okay. I'm sure some of you have got questions. So if you just want to speak, if we have a problem with too many people speaking, we'll resort to putting the hand up.
I have a question.
Please.
What about derived data? Like the uncertainty of an anemometer when it's mounted on a MetMask, you said it has a different uncertainty compared to a turbine.
Right.
But that uncertainty could be derived because you have your MetMask schema that says how long the boom is. Does it, so that you can use that information to validate whether it passes the IEC recommendations. So therefore, then you can calculate or derive your uncertainty. Should the uncertainties be stored in a schema or derived, or how does all that derived variables versus just storing them?
I mean, the short answer is that ontology can include variable transformations, so you can actually sort of encode these derivations in your ontology. I mean, the longer answer is it's part of your model. Like this theta parameter is essentially what you're talking about. Like you're calibrating parameters in your model that have to do with how uncertain we think things are, and we want to validate these parameters. So after calibration, we want to perform validation. So for example, you could have, I don't know what, some really good anemometer that you put up and then your anemometer, and you want them to, so you're making CDFs based on potential errors and measurements, and you want them to match. I mean, at the end of the day, after you've learned some method for quantifying uncertainty, you want to validate it. But I think that this transformation you're discussing, it can be encoded in an ontology.
An ontology, right? Okay, cool.
Thanks. Nice question. It's tricky.
I mean, I feel like it is an important distinction, though. Yeah, the uncertainties that we measured by doing a higher precision measurements compared to the uncertainty we get through uncertainty propagation and using our models, and these can be stored as different kinds of uncertainties in the ontology, and they're just different type of concepts that then later on, when you develop your own ontology for your own task, that's the role of a domain expert to be conscious of these things and to tell to knowledge engineering expert, oh, hey, I have actually two different kinds of uncertainties. These are two different concepts. They're two different classes that we have to define in our schema. They have two different names. These are their descriptions, so that later on, the person from outside that goes into and looks into the uncertainties, that is precisely why we need metadata and we need schemas. The person comes from outside and they look at it and like, oh, like this uncertainty, where does it come from? What does it mean? You go to the schema, you go to, if it is published especially, and there is like a description in English language, and you're like, oh, this is exactly what they meant when they said it. Like this value means exactly this, and this is importance of providing context and the meaning. Yeah.
I could not agree more. Like, exactly. There's, validation and calibration are very tricky, and it's best to rely on experts when doing it. But these things can be done in a trustworthy way, and you just want to maintain the nuance of that throughout the design process or throughout the data lifespan, and that can be accomplished through a comprehensive schema, which can be made modular through ontologies.
Julian, thanks very much for the presentation. If I want to see a kind of not too complicated, concrete implementation of an ontology, have you got any recommendations of like good places to start? Like I kind of get what you mean with the modularity and all this, but I think it would be, it would be useful to see an example of an implementation.
Totally. Yeah. And like part of the challenge is that ontology is a somewhat broad concept. So, I mean, a taxonomy can be an ontology. And I'm not sure if that would really be satisfactory to you or not. Like, I mean, you can sort of imagine taking a comprehensive taxonomy and making different schemas based on the things that you care about. And then if that's satisfying, then I can certainly point you to quite a few things that resemble taxonomies. It gets a little harder to find within the wind energy space. Ontologies that use these more exotic logical operators. I might point you towards the tech sector, data mesh, things like this. They seem to be a bit more advanced in exactly what they can do. And if I wanted to be sort of, look at the most bleeding edge thing, I'd point you towards Google. When Google has a robot scrape it against a website, it recognizes different parts of the website, say, oh, these are ingredients. Then it knows, okay, this fits into my bucket of an ontology, or sorry, of a recipe, and it can sort of use these logical operators to relate the contents of the website to what its concept of a recipe is. I'm afraid I don't have like the perfect answer, I guess. I think maybe if I had to pick one, I'd stick to my first answer, say, hey, like we can organize a bunch of different topics and concepts and then make schema out of them. And we can make different schema. It's a tough question. I hope I gave an okay answer. It's kind of it's just not very prolific in the wind energy sector. I might also point you towards the oil and gas data providers. They have a pretty good way of calling up the error or the properties of different data that they intake based on an ontology that they have.
Cool. Thank you. I'll drop you an email.
Great, thank you.
Maybe we can just tell Christian about or maybe Yuri, you can quickly tell Christian about the paper that we're writing, which is aiming to help people with questions exactly like that.
Yep. So as a part of Metadata Challenge, we are working on a paper that is aimed to do exactly that. One, explain these topics and ontologies like in a more approachable way for people in wind energy. Look at the ontologies that already exist, ontologies and schemas, or just conceptual data models in general. And provide like some simple examples people can relate to. And Julian is a part of that one too, of that paper. And we are as Julian said, it's a complicated topic, and it's the part of the difficulty of writing that paper was exactly like not to to condense it enough so that it's still approachable, but still capture the essence of it. So I can tell you that in the wind energy sector, there is a huge scope for development of these things. And if you want to look at people who successfully implement these kind of things, you have to probably look at e-commerce or medical sector. They are the ones that are really a bit ahead of other domains in this game. So
thanks. Something just came to mind actually. Car codes. I think that's a great example. I mean, you take any car to a mechanic, they plug in their little machine and they give you a code, and that code is universal across different car types and everything. And it follows a sort of ontology of different concepts in cars and how they relate to their car. So that might be the most concrete answer I can give out of the back of my pocket.
Cool.
You know what, I was wondering if you could answer, Julian, what do we actually do next? Like if we want these, okay, you're saying, first of all, you're saying uncertainty needs to be in metadata, but you're also saying we need to have some agreed upon domain ontologies, stroke taxonomies, stroke schema. What's your opinion on how do we actually get started on doing that now? I mean, we've talked about it a lot. We've kind of established what we need to do. What do we do next?
Yeah, it's a great point. I mean, our sector is that it's just so complicated. I mean, even the car code example, I'd say there's less in that ontology than we would really need for a comprehensive wind energy schema. We're seeing some really nice efforts in our task and other tasks and different organizations all over the world making different ways to organize data and concepts in wind energy. And to me, it really seems like just a bit of a business opportunity. I mean, whoever is able to have a comprehensive ontology will be able to be more strategic with the schema that they make, be able to organize their data in a better way. And it is a significant investment. I mean, it would take, I don't know how long to make a ontology for everything in wind, and even for like a large company. I mean, it would be a significant investment just to make an ontology for their own data. I guess I can only say like other industries have done this. It is something that can be accomplished. It is something that our more tech savvy counterparts like Facebook or PayPal have seen great value in achieving. But yeah, it is a significant investment in developing an ontology. And there's a gap right now where like more and more researchers are saying we should have an ontology. It'll be useful. We can develop modular schema. We can deal with the same variable names for different concepts in a sort of integrated workflow. But then the private sector comes and says, look, like I spend so much time already taking data from different sources in and making it fit into my conception of the world sort of through a data model. I could use more data models. We feel pretty far away from this like grand unification. And I don't know. It comes down to an investment. I think over the next 10 or 20 years, if you look at any organization or any large organization, how long they take ingesting data and matching it up to their conception of the world or their data models versus like how much time they'd have to invest in an ontology and then how much they'd save in terms of time invested, I think it would be a sound investment. But it is a significant investment, and I just don't think we're motivated enough as a sector to really do that yet.
But who will do it? Like, who should do it? Who's done it in other? I mean, there was an example of the oil and gas industry, but I've forgotten who actually did it.
Yeah. I mean, maybe there'll be some postdoc that makes a startup that is able to manage uncertainty for many players in the wind energy industry by a homemade ontology, and then they later use that ontology to create a data marketplace and become this major corporation. And anyone that wants to invest now should totally invest. I don't know. It's hard for me to say what the future will hold.
I feel like a lot of this comes to exchange of information, and when there is a need between different companies, like the more there is a need for different companies to exchange information, the more there will be pressure on those companies to adopt some kind of standard or IEA common data model, IEA common ontology. So let's say in the same automotive part, because there were very few entirely vertically integrated car manufacturers, because exactly they have to order, let's say, parts from different manufacturers. There is this great pressure to exchange information in a unified way. So I feel like it comes from there. Part of that, so that is part of the answer too.
Yeah, no, thank you. It jogs my memory. We've talked about this question before. Yeah, so car manufacturers was required by law. Like state lawmakers said, hey, like you have to have common car codes. And I mean, something similar could happen in our industry. We could have a lawmaker say, we need transparency. We're tired of not knowing who's responsible for what. We need a transparency through ontology. Then the other major avenue I see is a nonprofit, like the MPEG standard that was developed for digital objects like music files, things like this, was developed by a nonprofit that was a coalition. I think the MPEG standards for pictures, actually. Sorry, it was developed by a coalition of different people that deal with digital pictures, and they wanted to have a common standard, and they were able to achieve that by funding a nonprofit together.
Yeah, it is worth though mentioning that if we look back into like video standards and photo standards, that is by no means like a pinnacle of the greatest achievement. Like when people look into encoding or self-encoding metadata and stuff like that, it's and the whole idea of the encoders and decoders, it gets messy pretty quickly. So it's not an easy task to solve.
Yes, and I don't know. It seems like we're sort of developing an ecosystem of different schemas, different ontologies, and we just have to live in that ecosystem for now and make the most of what we have.
Yeah, you know me. I'm trying to look for ways of the best way to push it, or the best people, like the best way to make sure that ecosystem grows rather than stagnates. I think it's something that we could do in Task 43, in the organizing committee. That we could push something, right? So we could say, look, we definitely have to do this, or we should leave the ecosystem to keep doing stuff and see what happens, or we could push it in a certain direction. So that's kind of why I'm interested in that. Like, is there a direction that we can try and push it in that would help? But yeah.
Is it at all on the agenda of Task 43 to promote ontology development?
We were just writing the draft.
Should it be?
Yeah. I mean, we're just in the process of writing the extension proposal because it's being extended, and this is actually the opportunity to do that and to say we need. I mean, yeah, maybe I ask it differently to Julian. What would you write as what would you say should be done if we could say to Task 43, you should focus on this, and this? What should it be? Ontology development?
Yeah. I mean, actually, believe it or not, I've shared this opinion, but I'm glad you asked me. I'm happy to tell you. So we've developed a very nice data model for wind resource assessment. And I've heard only good things about it, and I've only have good things to say about it. It's a very nice data model. And I actually have a slide about this in my presentation. What you might be saying, well, what's a data model? Isn't that an ontology? And the ideas are very similar, but just maybe subtly different. I think the biggest difference is that the data model is sort of closed world. Like, it assumes a structure, and if you have new data, you need to fit it into the structure of the data model. While the ontology is more of this open world paradigm where you can allow for different schemas or different data models to be related to each other. So we've released a data model, and there is talk about a power curve schema. Like, that could be kind of a nice win. If we suggest a power curve schema, I think someone has a drafted schema already. Then if we do this thing, the next thing we could do is release an ontology relating the wind resource assessment data model and the power curve schema, and showing how these things can be put together. I mean, it's not uncommon to have power curve data and wind resource assessment data in the same ecosystem, and an ontology that we provide could put those things together in a very machine friendly way.
Yeah, it could do other stuff as well, though, couldn't it? We could think of other examples that we could focus on. But I think that's a really good start because it's stuff that's been done already within the task.
Thanks.
we should maybe talk about this topic more in the next Metadata Challenge meeting.
I'll make sure to attend next time.
I'll make sure to invite you on your proper email address. All right, 7 minutes left. Any other questions, comments, ideas?
Thanks for coming, everyone. It was really nice getting to share these things with you.
Yeah, thanks so much for talking and preparing such a nice presentation and taking the whole thing seriously as well. I definitely appreciate that. Your timing was perfect. Yeah, I guess there's just one last thing to say is that we have this digitalization event on the 9th of March. If some of you don't know about it, I think some of you are signed up. It's a hybrid workshop all day, taking place in Zurich. We have quite a few speakers talking about the challenges of digitalization. We hope to we're going to have a workshop, small group workshops where we try to solve all the challenges in 2 hours. So I'll just put the link in the chat if anyone fancies signing up for that, and it'd be nice to see some people in person. All right, then thanks everyone, and see you all next time. We'll be sending you the invitation to the next webinar in the next week or so, won't we, Yuri?
Oh, it depends if Kevin answers my email.
We've got quite a few in the plan anyway, in the pipeline anyway, haven't we? All right. See you later, everyone then.
Thanks, Julian. That was great.
Thanks.
Thanks.
Everyone. Bye. Bye.
Thank you.